Alexander Milovanov from Italy and Max Planck Institute Dresden. Talk. The title is Nonlinear Anderson problem.
Okay, thank you very much. And also many thanks to the organizers for inviting me here. It's a great honor to be here again and to give a seminar. So my seminar today will be given mostly from slides. I don't intend to give anything from the blackboard. And the reason for that is that I'm going to give a kind of a review of a problem that I find really very interesting and exciting. It's a nice problem both in theoretical physics and in mathematics, with a great physics motivation and at the same time leading to very interesting and nice mathematical models that are certainly worth studying. But, you know, if I give you only this motivation, I think that would be hardly enough and hardly be true. I found out that this topic of Anderson localization and Anderson problem is actually a very special problem for this institute here, for the ENEA. I mean, if you dig in the ENEA archive, you will find that there has been a specialized program devoted to Anderson localization, which was held July 2008 to December 2008, with many interesting topics that are directly relevant to what I'm going, if not to discuss, but at least to use in my role models. Especially those are spectral properties of the random Schrödinger operators. Another element, if you go to the list of Nobel laureates visiting this institute here, then number one is Anderson, Philip Anderson, after whom this phenomenon is named. And you can find his lecture in the archive from January 2008, where he presents his work and his discovery. And it's fantastically interesting to follow. And from that lecture also I learned that Anderson was chair of solid state physics group here at Cambridge from 1957 to 2006. So in many ways, this problem is native to Cambridge University. But not only this, by going to talks given during that program, I found that there was a talk by Shmuel Fishman from the Technion, who was speaking exactly on the nonlinear Anderson problem, which is the main matter of my presentation today. And you can also listen to Shmuel. If you open his lecture and follow it, you will see actually a great debate that started immediately from the start of his talk. People were literally interrupting him at every moment, whereas Shmuel was presenting something like equal time, as people say during the political debates. So presenting both pros and cons of the model he was presenting. So this is just to give you an understanding how strongly debatable and controversial the problem was at the time. Now, when I saw that, I had my blood pressure rise a little bit, because, I mean, if I myself involved with the Anderson problem, that is in many ways due to my co-author, Alexander Iomin, but I visited Iomin on the invitation of Shmuel Fishman in 2011 and 12. And I believe that despite that we started the work with Sasha in Italy, it would be literally not possible for us to bring it to a publication if I was not visiting the Technion on the invitation of Shmuel. Unfortunately, he passed away several years ago. It was a great loss to all of us. And Sasha, he is also retired now. And, you know, the nonlinear Anderson problem is still there. And this shows you what is science in them. So with these preliminaries, I actually proceed with the main matters of my talk today. And my plan is very simple. I give you a very short introduction to the linear problem first. I will assume, however, that most of you are familiar with this problem, so I will be very brief on that, showing literally 2 slides. and then I go ahead with the nonlinear problem. Then apparently I have much more material than the time ahead. So somewhere will be abruptly stopping myself, but I'm hoping to present you something at least that I find interesting and stimulating for future work. So about a linear problem. It was a seminal work by Philip Anderson from 1958, submitted to Physical Review in 1957. So absence of diffusion on certain random lattices. That was the work where he predicted the phenomenon, which was later in 1977 recognized as a Nobel Prize in physics. The prediction of Anderson is that if you have a random medium and you initiate a wave process in it, then there are some conditions under which this process cannot propagate to infinite distances and will get localized. This is a quantum phenomenon. So why it occurs? It occurs because a wave process will be reflected by the structural inhomogeneities of the medium. So you will get waves that are reflected and will go into destructive interference with itself, with the falling wave. And if the degree of the disorder is strong, then these interferences will occur on multiple paths, and the whole thing will be localized. Then there is a great discussion, actually, how all this depends on dimensionality of the imbine space. And that was also discussed during the program at ENEA. In the current way of thinking, basically it is proven by now that the phenomenon exists in 1D. Even if you have a small degree of disorder, small in the sense that you model it as a random field, but the amplitude of field might be even small, still you get localization. Then it's all a question of localization length. And the localization is exponential with exponentially decaying profile for the wave function, which means that this is strong localization. For 2D, the situation is similar. But for 3D, it's becoming less trivial in the sense that you will get localization only if the strength of random potential exceeds a certain characteristic level. But below that level, there will be no localization, and the linear field will still be not localized and will propagate to long distances. Now, what I'm going to present will be 1D, always 1D, but it will be nonlinear. And that is the main difference with previous works. So before I proceed, one comment on the phenomenon. It was observed experimentally. It was observed experimentally for many situations. Most recent have referred to light waves, and some people predicted this phenomenon for gravitational waves. It was also discussed for spin waves and for matter waves and for acoustic waves. So this is a question of how wave process propagates in a random environment. That's a characteristic of a wave process, of how wave propagates. So it's a universal thing occurring for any type of wave. I'm not quite sure if this phenomenon have been studied for turbulent plasmas, for instance. Well, some people predicted for turbulent plasmas, but I believe this is a kind of topic which even plasma physicists don't understand quite well. So I will not touch upon it. Now, from a mathematical point of view, in 1D, how do you describe the thing? Normally, people write Schrödinger equation, this one here. Okay, with the Hamiltonian. In principle, you may consider both discrete formulation and continuum formulation. Discrete formulation is a little bit closer to my way of thinking, since this is quantum phenomenon, and I like a discrete formulation for myself. Then in the discrete form, you have this fancy form. This is Laplacian operator, local. And epsilon n are random energies, which mimic the random potential due to the random medium. So then in this model, you have a full basis of states. So any wave function that you get, you may expand over a full basis, and you may normalize the basis functions and have some sort of normalization condition. Yeah, some sort of orthogonality condition. So you sum the basis functions and normalize them to the Kronecker data. So that's basically all preliminaries from the linear model. And I start with the nonlinear model now. The nonlinear model and the simplest formulation is just like you add a nonlinear term to your Anderson equation. And then the simplest formulation is like beta epsilon n squared psi n, where psi n squared is the probability density. So why you think that by adding this term, you might get something physically new? Because if you have a nonlinear term, then the wave function will be basically overlapping with itself. And from a physics point of view, it creates some sort of internal pressure. And this pressure will try to squeeze the field away from the localization point. So there is a chance that it starts to spread. Though it's not an obvious argument, of course. Yet people were asking, so does something non-trivial happens, first of all? If something non-trivial happens, does it happen for any value of beta, or there is some critical threshold above which, for instance, there is a spreading and below which there is no spreading? And eventually, if there is a spreading, then how it goes? That is, what is the dispersion law for the spreading process? At first glance, it appears that by adding a small nonlinearity, it will not really change anything to the field. Because if you are concerned with the asymptotic spreading process, then asymptotically, your field is very small. So even if it's spread over delta n states, then the amplitude of the field is 1 over delta n, the psi n squared. And if your linear thing is localized, then you simply add a vanishing thing to it. So what you can expect, only some vanishing addition to linear frequencies, vanishing frequency shift. But you know, this argument was quite used by people who were trying to establish Anderson localization for the nonlinear field. Then the opposite way of thinking is that things are not that simple. And in fact, they are not. So if you look more carefully, you will see that nonlinear frequency shift is basically beta divided by the number of states. But if your field is spread over delta n states, then the distance between normal modes, normally exponentially localized Anderson modes, it will also go as inversely proportional to the number of states, 1 over delta n. So the relative nonlinear frequency shift, which in this case is the Chirikov's parameter, the ratio between the nonlinear frequency shift and distance between normal modes, it will not depend on the number of states, at least if the nonlinearity is quadratic. Which means that if you have a beta value sufficiently large, in the sense that you allow for overlap of resonances, so your field is initially chaotic, this chaotic property will preserve through spreading, and the field will be chaotic all the time. And if it starts to spread initially, it will continue to spread up to infinity. And that is really what now is being established, what happens, that at least it seems that there is a critical beta value, which we can say roughly is of the order of 1, such that below that value there is localization, and above that value there is a abrupt transition to the localized state. So these ideas were first promoted by Bikovsky and Shipelyansky. It's a nice PRL paper published 2008. By the way, I saw that Dmitry Shipelyansky was attending this program on Anderson localization in 2008, though I could not find his presentation. Maybe I have to look more carefully, but I was quite interested to see what he was talking about at the time. Anyway, this paper was published in March 2008 and submitted in 2007. So it existed already by the time this program at INI started in July 2008. Now, I briefly introduce their argument. So they sustained that, yes, there is a critical value of beta about which there is a transition to delocalized state, and the spreading of the wave field is due to the fact that it is becoming chaotic. So the nonlinear Schrödinger equation is a chaotic system above a certain value of beta. Then the spreading is essentially due to coupling between the normal components that would be otherwise linearly localized by Anderson. And the coupling term is a triple term. So each Anderson normal mode, it will be coupled to 3 components. Then, if there are many components, and if the field is spread over a large number of states, and if it is chaotic, then basically this nonlinear term will work as a white noise term, and it will drive the spreading. And if it is white noise, then the amplitude squared of the noise will be the diffusion coefficient. And because on the other hand, there is normalization, there is conservation of the probability, and psi n squared behaves as 1 over delta n, then this guy here squared will behave as delta n cube, and this is the rate of spreading. And the rate of spreading then will also be connected to the fact that it is chaotic, so diffusive, and y writes ddt of delta n squared, that's according to the diffusion process. And this gives you a quite non-trivial quite non-trivial twist in this equation, from which you see that there is a scaling behavior such that delta n squared will behave as time to power 2/5, which means that there is a subdiffusive spreading law. And that was the main thing in the PRL. Literally, if you read that PRL, there are only 2 equations there, one of which is this scaling law. And that looks very nice, you know. When I read that paper, I was really admired. So simple argument leading to so non-trivial result. Really interesting. But what I think is a little bit more interesting here, that when you try to model it on a computer, you don't find the 2/5 scaling. And that was noted already by Pikovsky and Shepelansky. So yes, they predicted the 2/5 scaling from this simple diffusion argument. And then they put things on a computer and did the simulation. And they said, they clearly wrote on the PRL that, no, what we obtain from simulation is a different exponent. It's something closer to 0.3 instead, not 0.4, like 2/5, but smaller than that. And that they found non-trivial. No, you know, you should not be maybe dismissing that argument that we are talking about so minor difference between the exponents, 0.3 or 0.4. So what's the hell? The thing is that it's time going to infinity. So these are asymptotic laws. They are large times. And for large times, the difference will be notable first. Second, well, people also can say, so simple theory predicting clear exponent, then you don't see it in a simulation. But simulation is an intricate thing. In a simulation, you really don't know what means time going to infinity. You should know where to stop your simulation. So by how long time you should integrate, what is enough, where is enough, and how enough is enough. So one principally might be skeptical, say, okay, there is simple argument. There is no way to be mistaken about it. Simulation, okay, roughly supports the subdiffusive character of the spreading. Okay, these are points of view. Actually, a year after, in 2009, there was a paper by Flach et al. By the way, another competing group, actually, quite working in this area, who approached the same problem, but using a little bit different Hamiltonian, using the Hubbard model. And also, they did the simulation. And they say, well, we too see the exponent closer to 0.3. We don't see the exponent like 0.4. And also, they had some argument, theoretical, supporting the 0.3. Well, it was a little bit heuristic. I was trying to look into it. But well, the argument that 1.3 is somewhere. So from this controversy, the question arises, which is the true exponent? No, you know, things more or less converge to an idea that spreading is non-diffusive, it is subdiffusive, it's slow. But the question again is, what is the exact exponent here? And this is non-trivial. Well, one can be willing to understand the exact exponent because this is a mathematical problem and it should have an exact solution in the end. And it is nice to know the exact solution if we want to say that we know something about this field. But the discussion was quite controversial. There were more papers coming in, and there were some suggesting something closer to 0.4, others to 0.3. Until in 2018, there was a paper, PRE by Sinyanj and Skokos and Many who suggested still one more thing to it. They found that they can be also scaling with the exponent 1.2. So it's subdiffusion with half diffusion that they call in the jargon. And their argument was that, well, if chaos is strong, they don't explain what means to strong chaos. So if chaos is strong, then the exponent is 1/2, 1/2, so 0.5. And if the chaos is weak, then it is 1/3. But they still don't give an argument what means weak chaos or strong chaos. So they just say that there are two exponents, 1/3 and 1/2. All right, so you see the controversy and the spread in results has increased by that time. Well, I now gradually turn to my work with Sasha. It was 2012, and that is the work that we did at Technion mainly since the invitation of Schr&ouml Fishman. And our approach was just analytical. So we said, just let's go with strict mathematics. So what we know? We know that there is a basis. Then we can expand the nonlinear field over the basis functions. Then we substitute on the nonlinear Schrödinger equation. Then there is nonlinearity quadratic, which means that we just get this double summation. Then there is psi-n function, which gives third sum here. Then what we do, we multiply both sides of this equation by psi-n-k complex conjugate marked by a star, and sum over n using orthogonality. So this very standard business, of course. Then you get this nonlinear system of equations, which are the dynamical equations for a system of coupled nonlinear oscillators, quite standard thing. And the next point will be to take a careful look of it. I mean, so far it is really very standard. But let us take a careful look of it. We can be interested in an idea that there is a critical value of beta, about which there is a transport to long distances. So which is the minimal coupling then between the oscillators that can generate some sort of transport to infinitely long scales? And our idea was that we would simply rewrite this equation by singling out next neighbor couplings only. So the minimal coupling would be to couple only next neighbor oscillators. Then you can simplify the story and write the equation for next neighbor couplings only. And then you see, you can actually have a very nice geometric representation of the system of equations. And the representation is like this, that your nonlinear oscillator for a wave vector k, you just represent as a node. And each nonlinear oscillator is then coupled to its next neighbors. And the couplings are produced by these bonds. And there are 3 bonds here. So one bond is going to sigma k minus 1, another one to sigma k plus 1, and there is sigma k star. And star, the complex conjugate, indicates a falling wave, and those guys without star, they indicate the emitted wave. So at each node, you then get 1 falling wave and 2 reflected waves. And it goes, but it goes for all k. And then if you build it for all k's, then what you obtain a Cayley tree. So you can map your equations onto a Cayley tree, where each oscillator is given as a node here, and each oscillator has 3 bonds, so the couplings to next neighbors. And then you say that each oscillator can be in either a regular state, and here it is shown by empty node, or in a chaotic state, and this is the field node. And there is a certain probability to it. So there is a finite probability for an oscillator to be in a chaotic state. Then how you write this probability? You write it as a Boltzmann factor, of course, where this exponential minus delta omega over the nonlinear frequency shift. And in this business, the nonlinear frequency shift is characteristic temperature, which measures the chaotic property of the system. Then, because it is quadratic nonlinearity, this is nothing else than 1 minus over beta. So you will see then how it works. If beta is 0, so if your model is linear, no nonlinearity, then 1 over 0 is infinite, then p is 0. So the probability to be in the chaotic state is 0, which means that this thing is in a regular state, and a regular oscillator cannot conduct a wave process, so it is not conducting, absorbing. But if the nonlinearity is very strong, then beta is infinite, and then p is 1. So all oscillators are in their chaotic state. Of course, if you fill all oscillators, if you allow all oscillators to go into a chaotic state, then the system will be conducting. On the other hand, you might not really need that. You can say you can fill only a critical fraction of the oscillators to allow for the first time the wave field to propagate to infinity. And then you see that then you get a nice problem. This is threshold percolation problem on a Cayley tree, which means that there is a critical percentile of oscillators in a chaotic state, which you need to induce in order to allow the field to propagate to infinity for the first time. So it's percolation problem on a Cayley tree. But this problem has exact solution. It was quite studied in fractals since decades, since 70th, if not earlier. And there is a result to it, that the threshold percolation on a Cayley tree occurs exactly for the probability p being 1/2. And there is a nice formula for that, which is 1 over z minus 1, where z is the coordination number, and the coordination number is the number of bonds at each node. So we have 3 bonds at every node, zeta is 3, so it's 1/2. And on the other hand, beta is related to our nonlinearity parameter here through the Boltzmann factor. So equating this guy to 1/2, you get critical beta, like 1 over logarithm 2. And this gives you this nice estimate for beta, which basically you could expect because you have expected that this is the Chirikov parameter, so you would get something like in the order of 1. But well, it's 1 over logarithm to 1.44. And that is the answer for the existence of a critical beta. So from this, you will see that if you are below this beta, there is no way you can go to infinity because you're below the percolation threshold. If you are much above this beta, you propagate because everything is chaotic. It's a chaotic sea ahead. You go ahead. No, there are no obstacles to that. And there is just a critical way then when you can find a very complex path along a percolation cluster. And which is the dispersion law then at criticality. And the dispersion law at criticality is obtained immediately because it is known for percolation on a Cayley tree. If you put a random walker on a percolation cluster on a Cayley tree, then the dispersion law is subdiffusive, and it is written like 2 over 2 plus theta, where theta is what they call connectivity index. And in all this business, it is established result that theta is 4, the percolation threshold, and this gives you 1/3. And this is what people have seen in the simulation, starting from Pikovsky and Shepelyansky and so forth. But this is analytical. No one has found this thing analytically. We found this from this random walk on a Cayley tree. So that was my work with Sasha in 2012. Actually, our first work, which we started, and from which we really got excited that this is an interesting problem. We published some more work after that, but basically targeting some more technical aspects of the localization problem, but also looking into more complex nonlinearities. But that is in a sense for classical fields. You remember there was this work by Sinyansh where they said that there is also a room for 1/2 experiment. So if that can be justified in some form. No, our idea, it was also a paper which came in 2017 was to consider the quantum situation. And we simply argued that for a quantum field, there is no way you can write anything like a diffusive process, because quantum chaos would be much different from classical chaos. But what you could write instead is Fermi's golden rule. So the rate of spreading, which is still 1 over delta n cubed, would be not ddt of delta n squared, as diffusion equation would imply, but you write simply as a rate of transition between states, like in quantum dynamics would always write. And then this is ddt of delta n. And this would gives you delta n to 1/2. So apparently it gives the result that, by the way, the group of Flach found numerically. And they confirmed that from their numerical simulation of quantum spreading, quantum dynamics and random potential, the exponent 1/2 arises. And then this is consistent with this theorem. Next topic, which bothered, however, me and Sasha, and actually many other people, is still what is meant by subdiffusion. Why is subdiffusive? I mean, so far, I simply write you nice formulas from which you obtain a spreading law. It looks like a non-diffusive behavior. But which is the origin and the physics background for subdiffusion behavior? And there is a nice answer to it, actually very simple. So let us look into a quantum situation. So we write as ddt delta n, and this is the rate of spreading by conservation of the probability. Then do one simple thing, apply ddt to both sides of this equation. Then differentiate on the right-hand side. You obtain ddt delta n, and substitute this ddt delta n from the original equation you get here, and write the right-hand side in the gradient form. So as minus d delta n over something. So this something would then be a potential function. So this is just literally an equation of motion for a particle moving along the coordinate delta n in a potential field W of delta n. And this W field is of this form. It's minus something divided by delta n to the power 6. And you can immediately recognize this form as the attractive form of the Lennard-Jones potential. And this is celebrated potential. It occurs in molecular physics, where it is responsible for the existence of molecules. So it brings the different atoms together, and the potential that due to which atoms can be assembled in combined in bound states, the Lennard-Jones potential. But here it appears only as a dynamics of unstable modes, which has led us to a suggestion that there is some attractive dynamics in the nonlinear field. So the various modes can be attracted by each other and produce molecules in phase space. Now you ask me, what does it mean? It means a very simple thing in the end. No, you know, there are two maybe possible interpretations for that. One that I like a little bit more is that you have a sort of temporal analog of a phase transition. That is, when you have many coupled oscillators with a spread of frequencies, and if the spread is very large compared to the interaction frequency or to coupling frequency, then the whole thing behaves chaotically and produces a white noise. But when the spread becomes comparable to coupling frequency, then there is a spontaneous transition to a synchronized state. So these oscillators spontaneously synchronize, and they start to oscillate coherently through one single frequency. And this is to say that form clusters. So there is some sort of clustering of unstable modes in phase space. And this I see as a result of this attractive potential. Another interpretation is a little bit maybe more complex, and it refers to non-ergodicity of this process. Non-ergodicity, why it appears here? Because this is a spreading problem. For a spreading problem, by definition, you are dealing with something that is non-homogeneous. Non-homogeneous means that you have islands of regular dynamics and you have domains of chaotic dynamics. But when the whole thing spreads, it spreads into something that is initially regular. So there are only small areas of chaotic motion that appear at the boundaries of your expanding chaotic domain. But since they are small, they are then vulnerable against spontaneous synchronization. So they will be then producing with probability 1 domains of synchronized state, which will be clusters. And so they will be clustering. And clustering with the attractive interaction between modes will try to bind and to keep the unstable modes together, which would then impede them from spreading. And this slows down the spreading process. This is why it is non-diffusive. But you can do it now even more, put it on a more quantitative basis. So if you imagine a cluster of modes which interact through Lennard-Jones potential, then there is a probability, which is always written as a Boltzmann factor, for a given mode to quit the cluster after it has traveled delta n sites on it. This will be the Boltzmann factor, a squared to delta n 6, which is the Lennard-Jones potential. And you simply normalize it to temperature. Okay. And you can expand it since delta n is large. Then, if that is the probability to quit, then there is a probability to remain. And the probability to remain will be 1 minus. And then you get the probability to remain after delta n space steps. And then you want to translate it into delta t time steps. Delta t time steps, you know the dispersion law, you substitute and get a probability to remain on the cluster after delta t time steps, which is simply power law behavior, which is delta t to power minus 3/2. And this is exit time distribution. All then the dynamics becomes continuous time random walk with a waiting time distribution, which means that you have a random walk, but there is a distribution of times which have to elapse between consecutive steps of the random motion. So I think Sergei Fedotov would call that fractional Poisson process or something like that. So the CTRVs in general were quite studied in all this business. Then one writes a kinetic equation for diffusion, or subdiffusion with CTRVs with a distribution of waiting times, and that is quite well established. It results in a fractional generalization of the diffusion equation, where you get an additional operator on the right-hand side, which is the Riemann-Liouville derivative of order alpha minus alpha, where alpha is the exponent which appears on the waiting time distribution. So this gives you a nice kinetic picture for the behavior. No, in a sense, random walk process in the Brownian sense. You have in the Brownian random walk, you have a characteristic time. Here you don't have a characteristic time. Your mean time diverges. And that's it, that gives thing. So how much time I have now? 20 minutes. Okay. So I am more or less done now with this problem of quadratic nonlinearity. Now I will be going a little bit faster. You know, I have much more material and much less time. So I only address you to some other problems that were in the heart of our investigation with Sasha. And one of these problems was to generalize the nonlinearity. So to introduce a nonlinear Schrödinger equation with subquadratic nonlinearity. That is, so far, we were writing the exponent here simply 2. And at some moment, we decided to write here as 2s, where s is smaller than 1. So as any parameter between 0 and 1. And we consider this type of equation. Well, initially, we introduced it just as a mathematical model. We simply can write s and, well, say that we are interested enough to have a look at what happens here. But of course, this is not a great motivation because, first of all, the quadratic nonlinearity has its very precise meaning. It finds origin in the Landau, Ginzburg-Landau theory and in Taylor expansion over a small parameter. So quadratic nonlinearity is clear. What would be subquadratic nonlinearity is less clear. And basically, we were quite criticized by people who, well, they acknowledged our work, but they were asking us, what is the physics background for that? Well, we found this answer a little bit later. One thing here is it appears that this subquadratic equation is a compact form, an approximate compact form of a more general equation in which you have what we call distributed nonlinearity. So if you take a summation of n squared with a kernel which behaves as an inverse power law and sum, and you have actually a very broad wave packet, then approximately you can, instead of dealing with this complex nonlinearity, you can represent it as a subquadratic nonlinearity, and that is much easier to deal with. So that was one answer. But why this problem is interesting? It is interesting because if you go now to the Chirikov parameter, so that is the ratio of nonlinear frequency shift to distance between resonances, then now K starts to depend on the number of states. So before, when you had quadratic nonlinearity, 1 minus S was 0. You didn't get any dependence on the number of states here. And beta was then constant. So if you were chaotic from the outset, you continued to be chaotic up to infinity. But S being smaller than 1 or larger than 1 is a game changer. If S is smaller than 1, you see that K depends on delta n, and this grows with the number of states, which means that you initiate spreading, and it is, say, chaotic, but then chaos self-reinforces. So you're into a situation when your chaos becomes nonlinearly stronger as the spreading goes on. For S larger than 1, it's the opposite. It goes to a regular state instead. So from this point of view, S being smaller than 1 is a very interesting thing to study. And we started to look into it. But as soon as we did that, you know, there is immediately a mathematical problem, which to an average physicist is very difficult to deal with. That is, if you take your wave function, expand over basis states, and substitute into subquadratic equation, then what you get here, it will be a sum, this double sum, but rise to a power S, where S is smaller than 1. And mathematically, it is not quite obvious how to deal with this operator. We developed some first approximate approaches to address this nonlinearity and solve the problem in what we call leading order. And that work, which we published as PRE, actually showed that, strangely enough, there will be no spreading in first order. And spreading occurs only for quantum field, but not for classical field. And we were quite happy with this answer, but to a limited time only, since the idea that when strength of chaos increases with the number of states, it, however, conflicts with the conclusion that there is no spreading of the classical field. So there was something that started to bother us at some moment, at least beyond the quantum approach. So we decided to look better into this operator and to think what we can do about it. And then what we did, no, you know, suppose that S were an integer number. No, it is not an integer number, but suppose it is. Then we have multinomial theorem. And for any integer S, we can actually expand the nonlinearity into a multinomial series and write a formal equation here, a formal form. And into multinomial theorem, you would then take this summation of solutions to this equation, which is the sum of all indexes, which goes to S. And then you have your multinomial exponents, which are fine. And this is S integer. But this is not integer in our case. It's smaller than 1. So we said, OK, let us assume that we can write this formula, however. Then there is no problem with the multinomial coefficients, because factorial of S, well, we know that they will be gamma function. But what to do with the rest of the equation? And then we found that in principle, we can consider solutions to this equation here for S smaller than 1 in a sort of iterative sense. That is, assume first that a fractional exponent which satisfies this equation here is only one. Then we can solve this equation. It will be very simple to solve. There will be certain combinations of exponents producing S and other integer exponents whose sum will be 0. Then you say that the field must be, however small, not divergent. So then all integer exponents must be zeros, because otherwise they will diverge for infinity. This will result in a nice problem solved in terms of Diophantine equations. And you get your nonlinear term out of here. But this is when S is 1, there is only one fractional exponent. Then you say, let's go ahead and consider a situation when you have two fractional exponents and others are integers. And then on the next term, three fractional exponents and others are integers, and so forth. And surprisingly, you can build here an iterative procedure and predict your terms at every step of this iteration procedure. I cannot call it a perturbation theory approach because it is not a perturbation theory. There is no small parameter. But instead of having a small parameter, we had numbers of fractional exponents which come into play into our equations. And we can step by step predict the various steps of this approach. Now, you know, I put roughly on my slides the mathematical steps of this consideration. The only thing that my attempts to present this analytics to public through seminars failed so far in major situations. So I think I would fail also now, but I'm not supposed that you are going through all details. We wrote them as a PRE. And the result is very transparent, and it can be represented graphically. And that's what I'm going to present to you. So if I go graphically, you remember, I like to work first with some element of a Cayley tree. That led me to predict that there is a critical strength of nonlinear interaction. So something similar can be built now for subquadratic nonlinearity, but there is a difference. So what we have, in the first order, when there is only one fractional exponent, we built a Cayley tree, which will be always organized like this. There is only one bond which can conduct a wave, and other bonds will be something like counter sets because they will come with fractional powers smaller than 1. And if these are counter sets, they are disconnected, and disconnected set will not allow the wave to propagate. And this explains why in first order approximation we did not get any spreading, because we got this Cayley tree with disrupted steps anywhere. And we concluded actually erroneously that there will be no any transport anyway, since there is no transport in 0 in first order. But then, if you go to second order, instead of having a Cayley tree with coordination number 3, you get a Cayley tree with coordination number 5. And this Cayley tree is organized in a way there is always one conducting bond and 4 disrupted bonds, which are counter sets. And as a general situation, this will not conduct anything because all of them are disrupted. However, there is a possibility for special solutions. And there is a special solution here. And the special solution is that 3 out of 4 disrupted bonds will couple together and will produce a coupled state. And the coupled state, when it is produced as coupling between 3 disconnected bonds, can, for some values of fractional S, produce a conducting state, which means that in the second order, you get some states which will be conducting. So the field does not conduct in first order and does not conduct in 0th order, but in the second order it does. And apparently, well, it continues to conduct in all other orders. So if you go to the third order, you then obtain a Cayley tree with 7 bonds at each node, and there will be 6 disrupted, and 5 of which can organize themselves as a special solution, be coupled, and produce a conducting state. And this you can construct in every order up to infinity. And then you show that there will be always, in the end, a possibility of the nonlinear field to leak, but it will be leaking through these strange states which are produced through couplings between disrupted states. And this gives some idea, by the way, of non-local behavior in the system. If you have introduced a state which is coupling between identical states, it introduces something that you may perceive as non-locality. And in reality, it is becoming really non-local. Non-local because, well, when you start to look at coupling term and look into its scaling properties, the scaling properties will be such as to remind you about the Levy noise. So out of this topic, we have concluded that when S is smaller than 1, then there is a room for a situation according to which you don't have simply a Brownian noise which drives you the spreading, but there is a Levy noise. And Levy noise then produces you a kinetic equation with non-locality. So with Ritz-Weil operator, which accounts for the jumps along the coupled states. So along those strange states which we have produced through couplings between disrupted states and which work as non-local states. So our conclusion was that this system, however, is such as to allow the field to conduct, and they will be S smaller than 1, still producing some transport to infinite scales. Well, now this kind of insight. So you see that if S is smaller than 1, the transport equation, it will be this strange diffusion equation, which is different from the ordinary diffusion equation in that it contains Riemann-Liouville derivative over time on the right, and also a Ritz-Weil fractional derivative instead of the Laplacian. So it contains it counts for both waiting time statistics and jump statistics. And this complex statistics comes with complex coupling processes. So what does it mean to us in simple terms? It means that the asymptotic transport is given by t to power 1 minus s plus 1, where s, when it is equal to 1, it will be 1/2. We have seen this exponent from simple considerations involving the Lennard-Jones potential. So it is subdiffusive, but this subdiffusion has complex macroscopic organization. So it goes as a competition between waiting times, which work as to slow down the transport, and Levy flights, which work as to enhance the transport. So it is macroscopically complex. So then it involves strong and non-trivial couplings between special solutions, specially disrupted states, which means that the assumption dating back to Pikovsky and Shpelansky that you have a white noise driving force, it's basically not true. The assumptions, white is not true because white noise assumes randomness of the phases. There is no randomness of the phases. Why there is no randomness of the phases? Because it is nonlinear. You cannot expect random phases when you have actually non-trivial couplings between the modes. And this is the main conclusion. This explains why there is no 2/5 scaling. 2/5 scaling is obtained by assuming that there is random phase approximation. In reality, we believe there is no random phase approximation of this model. It is violated, and that is violated because to both the waiting time statistics and the jump statistics. This I'm all saying not as to criticize the work by Pikovsky and Shpelansky. They had a nice model. And you know, as they say, I think I remember what Patrick Diamond was saying, that all models are wrong, but some models are useful. So certainly they had a very useful model. It was useful because, well, it has led us to some very interesting consideration concerning the organization of transport in terms of waiting time and jump length statistics, which, by the way, also means that this is a wrong model because all models are wrong, as I said. But it was still interesting. So it's almost all about the subquadratic equation. I'm about to finish my talk. Maybe just in the remaining few minutes, I only give a insight into something that lies a little bit beyond this topic. So we were talking about subquadratic equation. Of course, we had this S parameter, which was a parameter which interpolated to us between quadratic nonlinearity for S1 and nonlinearity, non-analytical nonlinearity modulus psi n for S1 half. Then it has led us to rather a complicated analysis and to the necessity to go through all this forest of Cayley trees with many coordination numbers. But you know, if you limit yourself to S1 half only, then in principle you can solve your problem very easily. And moreover, this special case S1 half, it will correspond to what plasma physicists would appreciate as three-wave interaction between modes. So in plasma physics, we are used to some nonlinear processes. Essentially, that is the basics of quasi-linear theory. You may have nonlinear processes involving coupling between modes, and the coupling can be three-wave or four-wave. So in this picture, three-wave coupling is your nonlinear Schrödinger equation with S1 half, and four-wave coupling is nonlinear Schrödinger equation with S1. Then S1 is principally rather well understood. It leads to a Hubbard model and to some predictions of transport like time to power 1/2. And that is seen. But for S1 half, for three-wave interaction, there was no good theory actually in plasma physics. They applied these topics of three-wave interaction to predict turbulence spreading by three-wave interaction in a plasma. And turbulence spreading is another way to look at the nonlinear Anderson problem. But the thing is that in the specialized field of plasma physics, that was done using the Fisher's equation. It is sometimes abbreviated as Fisher-Kolmogorov, Petrovsky-Piskunov equation, FKPP. And that equation is actually a diffusion reaction equation. It is based on the idea that things are Gaussian, and they simply add some nonlinear sources and sinks to it, but they are Gaussian. But we know from immense number of experiments in plasma physics that turbulence spreading is not Gaussian. It involves some strange processes like tunneling of turbulence into regular areas, which is equivalent to Levy flight, or some non-trivial waiting time statistics. So somehow the Fisher's equation should not apply, but it leads to a scaling of turbulence spreading, to a scaling with the exponent 2/3, which people see in the simulation. And so they had to accept that, well, we are dealing with a apparently wrong model, but it leads to a very beautiful, correct result, which we can see in the simulation. So based on what I presented today, and actually it was my work with Jens Rasmussen, that there is no Fisher's equation actually for turbulence spreading, but there is nonlinear Schrödinger equation with S1 half. And this explains the 2/3 scaling seen in the simulation for fusion plasma, for instance. And this is really very simple since it is based on three-wave interaction picture, which is at the basis of quasi-linear picture. Well, so that is basically all. I can only add that for S1 half, you can build actually very simple model leading to a dispersion law, just repeating the ideas behind the Lennard-Jones potential. But to do that, you can do it really very simple. You write a Hamiltonian for three-wave interaction and write down canonical equations. And from canonical equations, you are immediate into the Lennard-Jones potential. And then you repeat your business with the spontaneous synchronization, with clustering, with waiting time statistics, which is again non-trivial and well-defined. And in the end, you end up with all these nice transport equations with waiting time and Levy flight statistics. So just to finish, we published quite really some papers out of it, starting from our first work in 2012 with Sasha, but they were quite some works with both quadratic and superquadratic and subquadratic nonlinearities, both on classical and quantum fields, and also in terms of its implication in fusion plasma and experiments, mostly with Jens Rasmussen at the end. So I can see here a very nice connection to topics that are now debatable or debated in plasma physics that are in the heart of realization of fusion quest, since it is important in fusion to know how turbulence can propagate or be localized in certain areas of a tokamak area. So this finds quite interesting application of this theory in physics with practical insights, how it should be organized or handled or controlled in specialized field. So one example, one mathematical problem, once occurring, not quite solved and quite heatedly debatable, had led to interesting insights into practical realization of fusion energy. So thank you very much. Yeah.
The equation you mentioned, how much you know or in your paper to explain the connection to.
You mean how FKTP equation arises? Well, one basically assumes that first, the propagate is Gaussian. So one writes a diffusion equation with Gaussian term. Then on top of that, one puts sink term and sources term. So sources are related with the excitation of new modes, and this can be made nonlinear. And also you can speculate a nonlinear sink. Then in some form, when sinks are compensated for sources compensate the sinks, so you get into a stationary state. And then you solve the equation, and then you get a power law form exactly at the point when you have compensated for sinks and sources. And this gives you the 2/3 behavior, which is justified in this way of thinking, but it is based on the assumption that it is Gaussian, and there is no Gaussian behavior. And this is, by the way, very heated area of discussion and fusion field, since, well, people are familiar with Monte Carlo simulation or with Fokker-Planck simulation, so they quite know what this diffusion operator is, and they like to simulate it. But as soon as you are done with something like Levy flights or waiting time statistics, it's not into their codes, and then it brings them into difficulty, and they don't know how to simulate that. They simply have experiment and see, well, we see the scaling, but we don't know why it works. So this solves the problem.